next speaker is David, telling us about enhancing symbolic execution with machine-checked safety proofs. David, the floor is yours.
Hi, so this talk will be about generating safety proofs, and this is a joint work with Shachar and Itzhaky. So I'll start with some background about symbolic execution. So this is a program analysis technique where we explore the paths of the program, and it has many applications, for example, test generation, bug finding, and verification. At the high level, it works as follows. We run the program with a symbolic input instead of a concrete input. And when we have a branch that depends on a symbolic value, and both sides of the branch are feasible, then we fork the current state. And then we continue to explore each of the new states. So let's see how it works with this example. We start with the initial state. Then we have this branch. So at this point, we don't have any constraints for x, which is assumed to be symbolic. So we fork the current state. Then when we follow the L side of the branch, we finish to run the program. And on the other side, we enter the block and execute this update of y. And then we reach the second branch condition. And this time, we do have some constraints over x. And so in this case, only one of the branch sides is feasible. And when we follow the L side, we also finish to export the program. So in this case, we explore two paths, and you can see that in each so in each path you have some you accumulate some path constraints, which will be used later. So in general, when we analyze a program with symbolic execution and we examine the results of the analysis, then we have several cases. So if the analysis found some bugs, then we can take the relevant the path constraints of the relevant buggy paths, use the SMT solver to obtain a concrete input, and then we can run natively the program to see, and you can see if there is a crash or not. Otherwise, if the analysis didn't find any bugs, then we have basically two cases. In the first case, we have a timeout, which means that the analysis tool didn't finish to explore all the path, and then we don't know if the program is safe or not. And in the other case, we have an exhaustive analysis, which means that the tool did finish to expose the path. But can we really claim in this case that the program is safe? So in general, the answer is no, due to several reasons. So first, the analysis tool can perform different forms of under-approximation, for example, state pruning and concretization. And of course, the implementation of the tool itself may contain bugs. So to convince you that this last concern is actually real, so let's have a look at this example. So we have two symbolic points, and then we compute the gradient between these 2 points. And now let's see what happens when we analyze it with the CLI, which is a state-of-the-art symbolic execution tool. So again, we start from the initial state, then we fork. And when we execute this division instruction, CLI checks for a potential fork because it checks if the divisor may be equal to 0 or not. And after this, the analysis is done. So what you can see is that we explored two paths and we didn't find any bugs. But is this program actually safe? So of course the answer is no, because sign division can fail in two cases. So the first one is when you divide by 0, and there is another case of overflow where you take the minimum sign value divided by -1. And this results in a number which is outside the range of signed int, and it actually results in a crash similarly to the first case. But it turned out that in CLI, the handling of sign division was incorrect, and the result it missed this path. So the bottom line is that if you want to have formal safety guarantees, you can't really rely on an unverified analysis tool. So what can we still do? So one way is to to try to verify the implementation of the analysis tool. But this is hard. For example, CLI is written in C++. It has complex dependencies such as the standard library, LLVM, and so on. So our solution is based on the idea of translation validation. So when we analyze a program, we additionally produce a safety proof, and this proof is specific to the programs that we analyze. So now the scheme looks like this. When we have an exhaustive analysis, which means that we finish to explore the path and there are no bugs, then we additionally produce a safety proof. In this work, the proof is written in rock, and then we can take the proof and validate it using the type checker of rock. So in this case, the TCB will contain, of course, it will contain rock and also the SMT solver. So now let's see what is the structure of the proof. So at the high level, we have two main sections. So we have the predefined section, which contains the semantics and the theory that will help us to prove safety. And the second section is auto-generated by the analysis tool, and it contains definitions and lemmas which are specific to the programs that we analyze. So let's start with the first one. So we want to define concrete and symbolic semantics. In this work, we deal with LLVM. So in the concrete domain, we have a concrete state, have a program location, have a store which maps variables to LLVM values, which can be integers or the special values undef and poison. And then we have a stack. In the symbolic domain, we define a state in a similar way, but instead of LLVM values, we have SMT expressions, and we also have a phi, which is the path constraints of the symbolic state. Here you can see several examples for rules for the semantics in both domains. So above you can see the rule for the sign instruction, which is quite similar in both cases. In the branch rule, so when we deal with concrete semantics, we can derive only one state depending on the violation of the branch condition E. And in the symbolic semantics, we always derive two states, and in each state we update the path constraints with the appropriate condition. And now we would like to relate somehow the concrete and symbolic semantics. So first we want to relate the states. So we say that a symbolic state over-approximates a concrete state if the concrete state can be obtained by evaluating an SMT model on the components of the symbolic state, while this model has to satisfy the path constraints. And then we have this theorem which connects between the semantics. So if we can reach a concrete state C from the initial state of the program, and in this sequence of steps we don't have any states that contain a Poisson value, then there must exist a symbolic state S, which is reachable from the initial symbolic state of the program, and S over-approximates C. So this theorem will help us later in another theorem which talks about program safety. And going back to our example, so we saw that we explored these two paths. So this structure is called the execution tree of the program, and basically it depicts the paths that we explored during the analysis. And now we want to define the notion of safety for trees. So we're in the context where we have a subtree where the root is S, and we say that this subtree is safe if these two conditions hold. The first, S must not be an error state. And then if we can derive S prime from S based on the symbolic semantics, then either S prime is infeasible, which means that the path constraints of S prime are unsat, or there is a child S prime prime of S in the tree, which is equivalent to S prime, and the subtree of this S prime prime should be also a safe. And based on this definition, we have this theorem, which is basically if the execution tree of the initial state of the program is safe, then the program is safe with respect to the concrete semantics. So This helps us to make a step toward showing program safety, but we still need somehow to compute this tree and to prove that it is safe. So this leads to the second section in the proof, which is done by the analysis tool. So let's see what we have here. So we have the definition of the program, the symbolic states that we explored. Then we define the nodes of the execution tree, and here we have here we prove that this tree is safe, and we do it in a bottom-up manner, which means that we first show that the leaves are safe, then we show that their ancestors are safe, and so on until we get to the root of the tree. Once we prove that the whole tree is safe, we can apply the previous theorem and conclude that the program is safe, again with respect to the concrete semantics. So the most challenging part here is showing that these subtrees are safe. So I will show you several examples to explain how it works. So suppose that we now execute this instruction. So we are in state S4 given here, and we want to show that the subtree of S4 is safe. So we look at the derived state, and now we have either to show that this state is invisible or find the matching state in the tree. So in this case, we go for the second option, and so we simply take the successor of S4 in the tree, which is given here below, and now we need to show that these two states are equivalent. So they are slightly different because of these expressions. So the analysis tools uses various SMT optimizations. So this expression is more optimized than the one given by the formal symbolic semantics, but we still see that they're equivalent. And in general, what we do to discharge these kind of goals is we formalize in ROC the SMT optimizations that are used in the tool, and we prove a level that shows that these optimizations preserve equivalence for SMT expressions, and then we just apply this lemma to handle these kind of goals. Another example, so let's see what happens when we execute this branch instruction. So we are in state S5, and it has two derived symbolic states. So let's start with the first one. So here you can see that the path constraints are unsat, so this state is invisible. And for the second state, so we want to find a matching state in the tree, which will be S7, given here. And now we need to show equivalence between these two states. This time we have a difference in the path constraints. So to handle this again in an automatic way, you have this lemma, which basically says that if the conjunction of PC and the negation of E is unsat, then we can remove E from the path constraint. So this helps us to discharge this goal. Let's talk a bit about proof compilation optimization. So as we know, RAW can be very slow when the proof is large. So to handle this, we use several optimizations. First, we try to reuse terms. For example, if there is an SMT expression that is used in multiple symbolic states, and we define this ROC term only once, and then I'll only use the variable in different locations. And another optimization aims to minimize proof objects. And I will spend a few slides about this one. So let's go back to the example where we have, so this was state S4, and we wanted to show that the subtree of S4 is safe. So what we did, we looked at the derived symbolic state, we looked at the state from the tree, the one that is computed by the symbolic analysis tool, and we had to show that they are equivalent. So let's try to see roughly how it looks in ROC. So we have this lemma. The goal of the lemma is to show that the subtree of S4 is safe. So this is just a reminder for what safe means in the context of trees. So safe is a relation, we apply its constructor, and then we need to show that each of these 2 points hold. So this block in the proof corresponds to this part in the definition. We want to show that this is not an error state, and then this block tries to prove this one, and we want to show this option, which means that we need to provide this child S prime prime. So the bottom line here is that the resulting proof is very long, and it uses expensive tactics like inversion and subs and so on. So if we do it for every subtree, this is going to be very expensive, so we want something better. So so this proof that we showed before for this specific proof for the subtree of S4, we can actually generalize it to this lemma. And this lemma is going to handle any subtree where we have an assigned instruction. So it can guarantee safety of the corresponding subtree. And once you fulfill these conditions, and the main thing here is that you need to show that the symbolic store, which is derived by the symbolic semantics, is equivalent to this sigma opt, which is the symbolic store which comes from the analysis tool. So this is the main part here. And once we have this lemma, we can make the previous proof much shorter. And so the proof is smaller, and we use simple tactics like apply and reflexivity. And the expensive tactics remain now in the proof of the generic lemma, but of course we prove it only once, and we reuse it for every subtree where we have an assigned instruction. And the same thing we do for other types of instructions like branch, call, ret, and so on. So a bit about the implementation. So we developed a formattation in ROC, roughly 20K lines. And in this work, we model a subset of LLVM with integers. So what it contains, so we have the semantics, concrete and symbolic semantics, and have also some theory, some of which we mentioned before. And then we extended CLI to generate proofs based on this formalization. So in the evaluation, we used several benchmarks with integers, so some examples for SVM comp and some other examples. And we focus on these metrics, so we want to see the overhead of proof generation, the proof time, and the proof size. So here you can see the results. So these two columns shows analysis time with baseline CLI and with our approach. And then you can see the proof time, which is basically the compilation time with the ROC, and the proof size. And so we have different modes. This column is the most optimized mode, and this one uses none of the optimizations. So you can see that there is a big difference in both proof size and proof time. And actually, in some of the cases, we even ran out of memory when we try to compile the proof. So these optimizations are essential to make things work. So to summarize, we proposed an approach for generating safety proof using symbolic execution, and we applied it for LLVM and the CLI. For future work, we plan to support more advanced features of LLVM like memory, etc. And also believe that this approach can be applied to other symbolic execution tools and to other types of program analysis. So that's it. Thank you.
Let's take a few questions while the next speaker sets up.
Thank you for the talk. So I was just wondering about the trusted base for this. So what do I have to trust when you know the V file gets verified, right? I probably have to trust that my C program was translated to LLVM, but then I have to trust your LLVM semantics. Maybe with something else.
Yeah, so we need to trust. So we have ROC, have our specification of the concrete semantics. You don't really care about symbolic semantics, only about the concrete. And we also need to rely on the SMT solver. This can be addressed by tools like CockSMT probably, but we didn't handle it in this work. And also, yeah, you're right about the translation from like the LLVM model to the embedding in ROC as well. Yeah.
You mentioned this bug in CLE,
Yes.
I think, that had to do with division.
Yes.
Did you find other bugs or some, symbolic
For this
execution?
work, no, but we found some bugs related to memory. Yeah. Yeah.
I think we should stop questions here and move on to the next talk. Maybe we can take other questions offline.